Hi everyone. In this video we're going to learn about measures of position and outliers. Just a reminder, things we've covered before. We talked about measures of central tendencies, which was like mean, median, and mode, and those tell us about a typical data value in our set. We also learned about measures of dispersion, which describe the amount of spread of our data. So now measures of position basically describes the relative position of certain data values within our entire set. So we're going to start with determining and interpreting z-scores. So the z-score just represents the distance that a data value is from the mean, but this is done in terms of the number of standard deviations. So basically we say we have a data value and we want to know how far that value is away from the mean, but we want to talk about it in terms of a number of standard deviations away from the mean. And so the computation is pretty straightforward. We subtract the mean from the data value and then divide by the standard deviation. We have our population z-score calculation and then our sample z-score calculation. The calculation is the same, it's just our notation changes. Remember, with population, mu represents the mean and sigma represents the standard deviation. And for a sample, x bar represents the mean and S represents the standard deviation. And so a z-score is unitless and it has a mean of 0 and a standard deviation of 1. So basically what the z-score will allow us to do is to compare different things, and we do that by converting variables with different centers of spreads to variables with the same center of 0 and a spread of 1. So first example, determine whether the Boston Red Sox or the Los Angeles Dodgers had a relatively better run-producing season. So the Red Sox scored 876 runs and play in the American League, where the mean number of runs scored was 731.2. The standard deviation was 72.6 runs. The Dodgers, who play in the National League, scored 804 runs, and this mean was 710.8, and the standard deviation was 60.2 runs. So notice we're comparing two different teams in two different leagues, and we have the mean values and the standard deviations, so we can use those in our z-score calculation. So we compute each team's z-score, and we're going to round to 2 decimal places. So for the Red Sox, we have our data value, which was 876. Subtract the mean, divide by the standard deviation. So our z-score is 1.99. For the Dodgers, our data value was 804 minus the mean over the standard deviation, and we get 1.55. So the Red Sox had run production 1.99 standard deviations above the mean, and it's above the mean if it's positive. It's actually below the mean if it's negative. And while the Dodgers had run production 1.55 standard deviations above the mean. So therefore, the Red Sox had a relatively better year scoring runs than the Dodgers. So basically what this is saying is if the average runs was 731, the Red Sox were scoring that season almost 2 standard deviations more than the mean. And comparing that to the Dodgers, they still scored way above the mean of 710. It was just not quite as much, about 1.5 times standard deviations away from the mean. Next, let's talk about interpreting percentiles. So the kth percentile, denoted P sub k, of a set of data is a value such that the k% of the observations are less than or equal to that value. So for example, the median is the 50th percentile, meaning 50% of the data is less than that percentile. And so the percentiles divide data sets that are written in ascending order into 100 parts. And then we have, if we look at this visual, P sub 99 would mean the 99th percentile, P sub 1 would mean the 1st percentile. And so let's focus on P sub 2. The 2nd percentile means that all of the values in our data set are less than or equal to that number. The 98th percentile means that 98% of the values in our set are less than or equal to this value, or that there's only 2% of the values are above that. So taking a look at one of the common uses for percentiles is exam scores. Jennifer just received the results of her SAT exam. Her SAT mathematics score was 600, and we're told that it's the 74th percentile. Well, what does that mean? Being in the 74th percentile means that 74% of SAT math scores are less than or equal to that score, 600. And then if you add up to get to 100, that means 26% of the scores are greater than that. So 26% of the students who took the exam scored better than Jennifer, and then Jennifer actually scored better than or equal to 74% of the people that took the exam. Next, we're going to determine and interpret quartiles. So quartiles are one of the most common percentiles, and it divides our data set into 4 parts, or quarters. And so we have quartile 1, quartile 2, which is the median, quartile 3, and then notice that that does divide our data set into 4 parts. So we have our smallest data value at the starting point, and then in quartile 1, 25% of the data. Between quartiles 1 and 2, another 25% of the data, and so on between quartiles 2 and 3, and 3 and 4. And then so if you're at quartile 3, notice what you have 75% of the data is less than quartile 3. So the first quartile, denoted Q sub 1, divides the bottom 25% from the top 75% of the data. And so you can say that the first quartile is equal to the 25th percentile. So you could say Q sub 1 equals P sub 25. The second quartile divides the bottom 50%, this is the median, the bottom 50% of the data from the top 50% of the data. So the second quartile is equivalent to the 50th percentile. So you could say Q sub 2 equals P sub 50, which is also equal to the median. And then the third quartile divides the bottom 75% of the data from the top 25%. So Q sub 3 equals P sub 75. The third quartile equals the 75th percentile. So finding quartiles. The first step, we have to arrange the data in ascending order. Then we have to figure out the median, because that's actually going to be our Q2, our second quartile. From there, we divide the data set into 2 halves. The observations below, which would be to the left of the median, and the observations above the median. The first quartile, Q1, is the middle or median of the bottom half of the data. And then the third quartile, Q3, is the middle or median of the top half of the data. So this is just how we're going to cut into 4 parts. We cut the data in half with the median, Q2, and then we cut the bottom half, the lower half, in half again. And that's going to give us our Q1 location. And we cut the top half in half again, and that gives us our Q3 location. So taking a look at this example, the Highway Loss Data Institute routinely collects data on collision coverage claims. Collision coverage insures against physical damage to an insured individual's vehicle. This table represents a random sample of 18 collision coverage claims based on data obtained from the Institute. We want to find and interpret the first, second, and third quartiles for collision coverage claims. Okay, so we're going to arrange this data in ascending order. That will be our first step. So the data is now written in ascending order. Notice this is our lowest number here, 180. The highest value is 21,147. Now there's 18 observations. So remember, when the data values, if the observations is an even number, the median is in between 2 values. We learned this before. And so finding the median, or the second quartile, we take the observation numbers, we divide by 2, and then for one of them, we add 1. So if we divide 18 by 2, we get 9th. data point, and then if we add 1, we get 10. And so our median is between the 9th and 10th observations. The other way to say that is it's just the average between the 9th and 10th observations. Okay, so all that being said, our Q2 is our 9th data value in our list when it's in ascending order, plus the 10th, and then dividing by 2 to get the mean. It's 1,805. So step 3, we need to do that same process again for the bottom half of the data and then again for the top half of the data. So the median of the bottom half for the first quartile would be Q1. So if we had just the bottom half of our values from our data set, notice it is an odd number, so there is an exact middle value. So the middle of our data here, our middle value point, is 735, so that's Q1. It's halfway between the beginning and the end of the bottom half of our data. The median of the top half of the data, which would be our Q3 or third quartile, same process. We take the top half of our data, those values, and it's an odd number, so there is a middle value. We don't have to do the average like we did with the whole data set. And so our Q3 would be located at the data value of 4,668. And so let's interpret this. The quartiles are percentiles. For example, the 25% of the collision claims are less than or equal to the first quartile. Remember, 25th percentile is Q1. So that's the $735 value. So 25% of the collision claims were less than $735. And that means 75% of the collision claims are greater than that number. And then if we look at another point, 50% or Q1, or the 50th percentile, 50% of the claims are less than or equal to that number we found in the middle, 1,805. And so that's our second quartile, and then 50% of the claims are greater than that number. And then our final quartile, Q3, which is the same as our 75th percentile, 75% of the collision claims are less than or equal to $4,668, our third quartile value. And the other way to say that is 25% of the claims are greater than that data value. Okay, so we found the quartiles. Let's go ahead and just line this up. So you can do it by hand, or we can type this into StatCrunch, or you can use Excel or the calculator. And we had 18 observations. The median we found was 1,805. The lowest value was 108. The max was 21,147. And then the first quartile we figured out was at $735. The third quartile was at $4,668. So remember, the median is the second quartile. So this is Q2. So now we're going to talk about what's called the interquartile range. So far we've learned about 3 measures of dispersion. They were range, standard deviation, and variance. And why we're now going to be interested in a 4th measure of dispersion, which is interquartile range, is because the other 3 are not resistant. If you recall, a measure is resistant if it's not substantially affected by extreme observations. An interquartile range is resistant. So interquartile range, IQR, is just the range of the middle 50% of the observations in a data set. So it's just the difference between the third and the first quartile. So if you split your data into 4 quartiles, then the inner 50% is between quartiles 1 and 3. So you just find that value by subtracting. So we're going to determine and interpret the interquartile range of the collision claim example. So our Q3 value, if you recall, was 46,680, and our Q1, quartile 1, value was 735. So the IQR, or interquartile range, is $3,933. So the IQR of the middle 50% of observations is 3,933. Now the mean collision claim was $3,874.40, but the median was 1,805. So the median is more representative of the center because the data is skewed to the right. Only 5 of the 18 observations are greater than the mean. Because we had such a large value on the upper end, that $21,147 value, that's what made the data skew to the right and which made the mean so large. So the majority of the values are actually less than the mean, and so we could use the median as a more representative measure of central tendency. So the range is, remember what we just talked about in the past, the range is the largest data value minus the smallest. So the range is $20,967. The standard deviation, if we calculate that, we would get $5,301.60. And then our interquartile range we just computed was 3,933. The values of the range and standard deviation are affected by that extremely large claim. And so when the distribution of data is highly skewed or contains extreme observations, it's best to use interquartile range as a measure of dispersion because it's resistant to these large extreme observations. Which measure do we want to report? Well, the shape of the distribution would be symmetric. The measure of central tendency would be the mean. And so the measure of dispersion would be the standard deviation. So this is all true if your shape is symmetric. But if your shape is skewed left or right, then you want to use the measure of central tendency to be the median, and then your measure of dispersion, instead of using standard deviation, we're actually going to go with interquartile range. Okay, so just to make this clear, if we know that our data is skewed either left or right, then we want to choose the median and the interquartile range to report our data. And in the future, if we read the direction, describe the distribution, it means to describe its shape, skewed left, right, or symmetric. It means also to describe its center, either mean or median, and its spread, either the standard deviation or the interquartile range. The next thing we're going to do is to check a set of data for outliers. So outliers are these extreme observations. So when performing any type of data analysis, we should always check for extreme observations in the set. Extreme observations are referred to as outliers, and they can occur by chance, because of an error in the measurement of a variable, during data entry, or from errors in sampling. So there's a number of reasons why we might come across outliers. So checking for outliers, step 1, determine the first and third quartiles of the data. Step 2 would be to compute the interquartile range. Step 3, determine the fences. Fences serve as cutoff points for determining outliers. And so here's a calculation for the fences. The lower fence, you find that by taking the first quartile and subtracting 1.5 times the interquartile range. So upper fence, third quartile, plus 1.5 times the IQR. So you have to find the first and third quartile, you have to find the interquartile range, and then you plug them into these formulas to find the fences. And then step 4, if a data value is less than the lower fence, so basically on the left of the lower fence, or greater than the upper fence, or on the right of the upper fence, it's considered an outlier. So let's try that. We're going to check the collision coverage claims example for outliers. So our first and third quartiles, we had done that work earlier. Q1 was 735, Q3 was 4,668. The interquartile range we computed as well. It was at 3933. And so let's find the lower fence. So our quartile 1 was 735. Our IQR, interquartile range, was 3933. And so we say 1.5 times 3933 and subtract that from 735. That's where this number came from, negative $5,164.50. The upper fence, very similar, but we add to the third quartile. So we have our IQR, 3933, times 1.5, and we add that to that 4668 number. So our upper fence is $10,567.50. So there are actually no observations below the lower fence. In our data, if you go back, there was no numbers lower than our lower fence number. But there is an observation above the upper fence. It was that very large claim value of that $21,147. So we can conclude that that was actually an outlier. Okay, that's it for this one, you guys. Thank you for watching.